Wait 5 minutes. ¿Cómo se llama la licenciatura de Estados Unidos? ¿Cómo se llama? Ciencias de los materiales. ¿Así se llama? Él sí hizo maestría. Eso sale por este así es la que se The next topic, hydrothermal synthesis and characterization of hydroxyapatite macrostructures. Yes, thank you.
Good morning to all. My name is Karthik and I'm working in University of Autonomous Hidalgo. So I'm going to present a part of my work. This is the synthesis and characterization of the hydroxyapatite microstructures by using hydrothermal method. So I will explain primarily the objectives and the background and methodology, results and conclusion. So the main objective of this work, as says in the title, so synthesize the hydroxyapatite using this precursor as the calcium hydroxide ammonium phosphide method. Here we found the effect of the pH, so over the structural properties. So we increase the pH using the nitric acid, and we decrease the pH. Sorry, we decrease the pH using nitric acid, and we increase by using ammonium hydroxide. And we left the remaining parameters constant in this part of the work. So the temperature of the hydrothermal oven is 200 degrees centigrade, and the time is 24 hours. And the concentration is stoichiometric. I will explain the stoichiometric relation later. RDCM and EDS to confirm the phase and the composition of the hydroxyapatite. The hydroxyapatite is ceramic. The ceramic is metal oxide ceramics, and another is the calcium. Literally more bioactive, and hydroxyapatite falls in the calcium phosphate family. So the metal oxide, or generally the metal oxide ceramics like aluminum and zirconia are used for the joints between the bones and other things. but they are less bioactive. They are more corrosion resistant and more harder compared to the calcium phosphate. But these are having more chemical composition very near to our human bone. So they are used generally for the refilling of the teeth or for other bone structures in the body. The hydroxyapatite is generally the 69% of our bones are of hydroxyapatite, and of the material hydroxyapatite, the remaining are other organic matters. So this can be also prepared by laboratory process, which we try to do now, and it has many applications. Generally, the hydroxyapatite formula. Okay, I will explain later. So the main applications of the hydroxyapatite are which is used as a remineralizing agent in the toothpaste and the fluorescence material. It is used as an ionic conductor and especially in gas sensors due to the defect of the OH, which is the hydroxy part. And it is a thermoluminescent material. Around 180 degrees centigrade, it has a luminance properties. Generally, catalyst also in many biomedical applications. And generally, we know the synthesis of the materials is physical and chemical, and this is very common. So here is another kind of dividing like dry methods and wet methods and high temperature process and using the biochemicals. Which comes under the wet methods where we use a solvent. So in case of dry method, we need solvents to use. So here the advantage of the hydrothermal is we increase the temperature to 200 degrees centigrade and maintain the pressure less than 1 atmosphere. The solvent not to evaporate and have a more homogeneity compared to at the room temperature between the solutions, which makes us to form the precipitates which is more homogeneous and controlled size. So here, one calcium. So this is the formula of the hydroxide. So here the stoichiometric relation should be this is the ratio where it should be the 6 of the phosphate and the 10 of the calcium. You know, of the phosphate and the calcium oxide, and then we mix in the denized water, and the pH of the solution without any addition of nitric acid is generally 9.6. pH using the and we increase using the and we kept inside the hydrothermal oven for 24 hours at 200 degrees precipitate, and then we dry it at 50 degrees centigrade for hydroxyapatite powders. So these powders we have, these are the uncalcinated powders, and we have calcinated at 500 degrees centigrade in order to observe the effect of the annealing temperature. Hydroxyapatite powders before calcination. So you can see all around 5 to 40 micrometers, and we can see addition of nitric acid. It makes some porous structures, but really they are totally agglomerated because they are not calcined. So there are a lot of residues on the surface, agglomerate and form the larger grains compared to and there is no much difference between the pH, the grain size. So PDS analysis. So to confirm its calcium to phosphate ratio, a stoichiometric hydroxyapatite should have a calcium to phosphate ratio of 1.67. In each case is around more than this, more abundant calcium. So obviously it is calcination is necessary, or it's a compulsory process to evaporate the calcium part reduced due to the phosphate and hydroxides. So these are the X-ray patterns of this is as prepared, and this is with the nitric acid and ammonium hydroxide. So we can see especially the peak 112 will add this, which makes it less structurally defective without any changing with another acids or hydroxides. All the peaks corresponds to the hydroxyapatite, and the preferential orientation is 2-1-1. And these are the semi-images of after the calcination at 500 degrees centigrade. So we can clearly observe the particle size is around 50 nanometers to 2 micrometers. These top 3 images are set for nitric acid with 7, 8, and 9. Any addition where the particle size is around from 9 to 40 nanometers. So in order to observe more clearly, we did the ASM analysis, where we can see increase in the pH try to form the microstructures like rod-like structures of hydroxyapatite, and these values denotes the particle size. So here you can see the pH 8 and the pH 9.6 are around 90 to 86 of similar particle size from 15 to 18 nanometers. Particle size of smaller, and there is another range which are really big of the particle size, and we can see for pH 8, yes, there is more homogeneous distribution compared to other. And these are the extra pattern and the FKR of the different pH values of the hydroxyapatite structures. So we can see here it presents all the peaks of the hydroxyapatite, and in the first glance hexagonal, but we did the rest of the XRD, two different phases Rydberg analysis, where we can get the weight percent of the each phase present in pH. The maximum phase that is presented here is in the hexagonal. So this is an unstable phase which forms from 300 to 600 degrees centigrade. So the next step is which we are going to do is to calcinate at higher temperatures around more than 600 or 700 hexagonal phase, and we calculated using the Taylor formula in each and every phase for each and every pH. Like image of the minimum particle size is observed, minimum crystal size is observed for the pH 8 with nitric acid. So even in case of AFM, we can observe it has more homogeneous distribution with particle size around 15 nanometers. So which is in coincidence with the crystallite size of time. And FTR spectra show these are the FTR spectra. Here we don't see much difference, but all the phosphate groups are present. And this carbonate is due to the absorption of the CO2, the atmospheric CO2, very less compared to the other phases which we observe. So I conclude that the same analysis before the calcination, we have very wide range of nanoparticles or microparticles from 5 to 40 microns, but after the calcination, it reduced it to around 15 nanometers. And the EDS analysis confirmed that they are more calcinated, and we believe that that it has evaporated and started to form the monoclinic phase after the calcination. So further calcination is necessary to get the pure hexagonal phase. Before the calcination, the XRD confirms the increase in the pH is reduced to the crystalline structure or the structural properties of the hydroxyapatite powders. So in future, we will be selecting a sample and try to calcinate for the gas sensors and thermometer. And thank you.
Thank you. Any question?
Does the increment in calcium, is it good for the biocompatibility of the material?
It may be, but we need to do the real measurements to know how much it is good. So generally, have high calcium in the powders which we prepare, because it may depends on application, because we are mainly focused on gas sensor and thermonuclear. So for bio, maybe yes.
I have a question. So what is the shape and the form desired application?
For well, the size which we want is the more smaller now, because to have high surface area for then the gas absorbs mainly for gas.
What size?
Around 30 to 50 nanometers or something. So the size, yes, we have obtained very less size, but the shape, it's more preferable to have rod-like structures, but because it will have higher surface area, but we didn't observe yet.
Thank you. Karthik.
Thank you.
Jacob Morales. Wait 10 minutes.